In this video, we're going to put away the vector notation just for a little bit, and we're just going to look at straight line motion with constant and variable acceleration. So this falls under the branch of kinematics, the study of motion of bodies, objects, particles, and today we're sort of doing the baby steps, the first introduction to this in what we call rectilinear motion. So rectilinear comes from the, so it's got the prefix of recta, which means straight, and so this is motion in a straight line. All objects are treated as points. They don't change shape, they don't rotate. So if we look at this image up to the right here, we can see point P will have a position coordinate of x. So I could read off that value, and it's going to tell me exactly where the point P lies. So looking at this image down here, we could see that point S, which is our starting point, is at x equals 0. We then follow this line across to the point A, which is x equals 4, and then go back the way we came, but a little bit further to get to x equals negative 2. So when looking at this, if we were just interested with distance traveled, to get from S to F, we've gone 4 units and then 6 more units. So in total, we've traveled 10 units. If this was a hike that you were doing, like if you were walking down a beach and then you walked back up it, you will have walked 10 kilometers. But you're only 2 kilometers away from your starting point. So the displacement that you have is 2, but that's not the whole picture. Remember, displacement also gives us direction. So we need to add negative 2 because we're 2 backwards from our initial direction that we chose. So this is positive x going to the right. Our average velocity. So in this image here, we've got changes in x depending on time. If we were looking at this average velocity that we've traveled over the course of that, we use our gradient function. So change in position over change in time, rise over run. So that is what we call delta x over delta t. Let's try and draw that delta a little bit better. Delta t, which if you're familiar with your gradient formula, can also be written as x2 take x1 over t2 take t1. If we want the instantaneous velocity, so that's this pink line here, we then want to take this a step further. Make dt tend towards 0. Looking at that derivative from first principles, this gives us the instantaneous velocity, which is the derivative of x with respect to time. If we then want acceleration, we take that one step further. We take our velocity and differentiate it with respect to time. And we see this pattern that we have. To go from displacement to velocity, you're going to derive, so d dt. If you go from velocity to acceleration, you're going to derive. But then if you're going the opposite direction, you're going to integrate. So we're given example 9. The velocity of an object, which is initially 3 meters to the left of O, is given by v of t is equal to 3t squared minus 2t minus 5 meters per second for positive values of t. We want to determine the displacement from O at any time t. So just reading this question, I want you to think about what is this initial 3 meters telling us? It's our clue as to what our constant of integration is. It's the information that they've given me to solve for c. So I'm going to put that in the forefront of my mind and then come back to it when I need it. So starting with part A, we've got the displacement from O at any time t. So to find the displacement, let's go back up to our graph. I've got a velocity I need to integrate with respect to time. So r of t is equal to the integral of v of t dt. But you can see I've already fallen back into my vector notation, but we're not actually using r of t anymore because we've only got one position. There's no y coordinate. I can just write this as x of t. So x of t equals the integral of velocity with respect to time. So if we integrate that 3t squared, we're going to get t cubed. If we integrate that 2t, we're going to get t squared. And if we integrate that 5, we're going to get 5t. And then we'll have our constant of integration. So we know that x of 0 is equal to 3. So we substitute that into our new formula, and we find that 3 is equal to 0 cubed minus 0 squared minus 5 times 0. So we just get that c is equal to 3. So therefore we know x of t is equal to t cubed minus t squared minus 5t plus 3. For part B, we're asked to find the acceleration. So we know that that's just dv dt, which in this case is going to be 6t minus 2. And that's going to be meters per second squared. And down here, that would be meters for our displacement. We want to find when is the object at rest. So if you're at rest, your velocity is equal to 0. So what are the values of t that satisfy the following? V of t is equal to 0. So we get 0 is equal to 3t squared minus 2t minus 5. So to do that, we want to find the factors of that. So the factors of that polynomial are going to be 3t take 5 and t plus 1. So we can see there we'd get 3t minus 5t, which is going to give us that negative 2t. So we know that t equals 5/3 of a second, or yes, 5/3 seconds because it's greater than 1, or t equals -1. But hang on, back up here we said t has to be strictly positive. We're not saying what happened 1 second before we started even calculating time. We can't see in the past. So, but t greater than is equal to 0. So we reject that second solution. So only the first solution is valid, which means it is at rest after, let's say 1 2/3 of a second. Part D is asking us to find the distance traveled in the first second. So distance traveled is just going to be a difference in our x coordinates. So we want to check how did we go if we compare x of 1 to x of 0. We also want to check what direction is the velocity moving. So if we were to substitute in 0 to our value of v, we can see that it's got -5 meters per second. So we have that it's moving to the left. If we substitute in v equals 1, we're going to see that it's -4 meters per second. So we can see that the distance traveled will equal the magnitude of the displacement during the first second, because we're not turning around between the 0th second and the first second. So we can just apply this x1 minus x0, which is equal to the magnitude of 1 cubed plus minus 1 squared minus 5 times 1 minus 3. So that's going to be -8. And we've got x of 0 is -3, so minus -3. That's going to give us a displacement of -5, but we want to find the distance, so it's going to be 5 meters to the left. And the last thing we're asked to find is the acceleration when the velocity is 0. So we know the velocity is 0 at this point, 5/3 second, so we're just finding a of 5/3. So substituting that into the equation that we found, we get that a was equal to 6t, so 6 times 5/3 plus 2, I believe it was. Let me just check. Minus 2. So 6 times 5/3 is just 2 times 5, so that's 10. Take 2, so we get an acceleration of 8 meters per second squared, and that would be going to the right. So when velocity is 0, acceleration is 8 meters per second squared to the right. We have another example here. a particle moves from rest with constant acceleration, reaching a speed of 20 meters per second in 8 seconds. And we want to calculate the acceleration and the distance traveled by the particle. Starting off with the information we're given, we have that we reach a speed of 20 meters per second in 8 seconds. So if we looked at the average acceleration, that's going to be the change in velocity over the change in time. So that's delta v delta t, which is equal to 20 take 0 because we started at rest, and then we've got 8 take 0 because the starting time is t equals 0. So this gives us 2.5 meters per second squared as our average acceleration. So we give that as a of t is equal to 2.5, and we use that to develop our velocity and our other components. So if we want to get from acceleration to distance, we first need to develop v of t, which is just going to be the integral of a of t with respect to t. So that's just going to be 2.5 t plus c. We know that it starts from rest, so that means it's going to have v of 0 is equal to 0, so therefore c is going to have to equal 0. And then we get x of t is going to equal the integral of v of t dt. So that's going to equal 2.5 t squared on 2. The other way we could write that is 5 on 4. So 5t squared on 4. We're going to get another constant of integration. What would we consider the initial movement? Well, it's going to start at a starting point, and that starting point is our reference for every other point. So we just take x of t is equal to 0. We're not told it's in any specific position, so we're going to get that c is also equal to 0. So we get these final three equations, which is the acceleration is constant, 2.5 meters per second. Notice how there's no value of t here. That shows that it's a constant. Then we get velocity, which is just 2.5 times t, and we get position, which is 5t squared on 4. So we're asked to find the distance traveled by the particle in these 8 seconds. So we're just going to find x of 8. Because we start at 0, we don't need to take away x of 0. It's just going to be the value of x of 8. That's going to be 5 times 64 on 4. 64 on 4 is just 16, so this is going to be 80. And then our units are meters. So this is 80 meters. That's the distance that's been covered. Last example for the video, I believe. Yep. We have a ball thrown directly upward from a platform 16 meters above the ground. So this is giving us an x value that isn't 0 as our starting point. So it's 16 meters above the ground. So there's our ground. Here's our starting point. It's going to go straight up, and then it's going to come straight down. Right? That's what we've seen all our lives. And it's going to have an initial velocity of 24.5 meters per second. So what is the information that we have? What can we determine? So we know that the acceleration of an object moving through the air is going to be gravity. And gravity goes in the downwards direction. We've observed this our entire lives. We didn't know why it happened. We've just seen it. So we know that our acceleration is constant. It's negative 9.8 meters per second squared. So how do we find our velocity? Well, we just integrate that. So integrating negative 9.8 with respect to t, we're going to get negative 4.9. Oh, no, sorry. I'm skipping ahead to the position vector. We want negative 9.8 t. So we also have that constant of integration, but we can solve that using this initial velocity. So we know v of 0 is equal to 24.5 meters per second. So therefore, negative 9.8 times 0 plus c equals 24.5. So C is just going to be equal to 24.5. So we're asked to find the time that we reach the maximum height. So that's going to be this point here. And notice if it's going up and then it starts falling down, there's going to be a point where it goes from positive velocity to negative velocity. And to get from positive to negative, you have to go through zero. You can't just jump over it because it's a continuous line, right? So we can just find when is v of t equal to 0. So v of t is equal to 0. That means we have negative 9.8t plus 24.5 equal to 0. So take 9.8 to the other side. T is going to be 24.5 divided by gravity, which is equal to approximately 2.5 seconds. So it's going to take 2.5 seconds for the ball to reach its maximum height. Part B is asking us to find the maximum height above the ground. So what we do is we develop x of t and then substitute in 2.5 into x of t. So x of t is just the integral of v of t. So in this case, it's going to be negative 4.9 t squared plus 24.5 t, and then plus a constant of integration. So we know that it started at 16 meters, so x of 0 is equal to 16. We get, therefore, 16 is equal to c. Because we're working just with polynomials here, we're never going to have c not equal to the value of the initial. But if you're working with like a sine curve, in that case, you could have c values that weren't just the initial. Because in that case, you can have t of equal to 0 give you a non-zero solution, like cosine of 0 is equal to 1. Okay, so we have our x of t. We want to then calculate what is x of 2.5. And that just gives us a value of 46.625 meters. So we know that this distance here from the top of my ball's trajectory and the ground 16 meters below my starting platform is going to be 46 meters approximately. Part C is asking us to find the total time the ball is in the air. So all we need to know is when does the ball reach the ground? So when is x of t equal to 0? So we let 0 equal the equation that we just developed. So that's going to be 4.9 t squared plus 24.5 t plus 16. And so I don't think that this is factorizable because we've got non-integer and not easily put into fractions a, b, and c components. So I'm just going to use the quadratic formula. So finding the values of t, we're going to get 5.585, or t is equal to negative 0.585. And we know that t is greater than or equal to 0, so we ignore that solution, and we're just looking at that 5.585, and so it's going to take 5.585 seconds to reach the ground. Okay, part D is asking us to find the time taken for the ball to fall to the ground from... The time taken for the ball to fall to the ground from the maximum height. So that's once it's reached its maximum height, how long does it take to fall this 46 meters that we found? So all that's going to be is our total time, 5.585, subtract our maximum time, which was 2.5, which is just going to be 3.085. 3.085 seconds. Part E is asking us to find the speed of the ball when it hits the ground. So that is going to be v of 5.585. So you can see once you've developed all of these equations, the rest of the questions end up being just a substitution. So that's negative 9.8 times 5.85. Anyways, that's going to give us negative 30.23. But that negative sign is indicating the direction, right? It's falling down into the ground. So our speed is equal to the magnitude of velocity, which is positive 30.23. And then lastly, part F is asking the speed of the ball when it returns to the level of the platform. So we first need to find when is x of t equal to 16. So we know it's equal to 16 when t equals 0, but the other time is from the equation. So if we take the 16 to the other side, we cancel out that value of c. We're left with 4.9 t squared negative plus 24.5 t. But remember, this 24.5 t we can factorize out t. So that's where our zero solution comes from, is that first factor, and then our second factor comes from this bracket here. So solving that for a value of t gives us t is equal to 5. So 5 seconds. So once it comes up and then it goes back down to be in line with that platform, that's going to be, that path is, or let's do it in a different color. This path it takes is only going to take 5 seconds. All right, so that is all the examples for this video. Thank you very much for watching.